Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 4, Climate Matrices and Linear Algebra. In this video, we will review matrix algebra and discuss an SVD representation model for space-time data. Let's begin by creating a matrix. We are going to be using the NumPy module accessing the mat function. Just a reminder that the matrix notation in Python requires you to use that mat function in the NumPy package, and your matrix is going to be set up in an array of arrays. So you're going to want to have your outer array followed by an array of your first row, namely in this case 1, 2, closing that first row array, and then following it with your second row array, which is namely 3, 4, producing the matrix seen in out 2. We can also do matrix subtraction using this NumPy mat function. So we have a matrix that has rows 1, 1, followed by 1, negative 1, and we are subtracting the matrix that has rows 1, 2, 3, 0, resulting in the matrix found in out 3. We can also do matrix multiplication using this NumPy mat function. We're going to have our first matrix being 1, 1, 1, negative 1, and we are going to multiply this by the matrix of 1, 3, 2, 4. So we do get a matrix as seen in out 4. Just a reminder on matrix multiplication, the way you would figure out this first element of the output matrix is you are going to multiply 1 times 1 plus 1 times 2. And that is because this 1 and this 2 make up the first column of our second matrix. So we are truly doing matrix multiplication. Another example of matrix multiplication, we are just going to switch our two matrices used in inline 4. In this one, we would get this element of 4 by multiplying 1 times 1 plus 3 times 1. Which does result in a 4. So order does matter when you are doing matrix multiplication. In order to yield a matrix inverse, we could go into the NumPy package, accessing the linalg module within the NumPy package, and then further accessing the INV method. This INV method will find your matrix inverse. Just use a matrix as your parameter, and you will get the inverse out of the matrix as seen in out 6. If we wanted to verify that result of the inverse, we could go ahead and do some matrix multiplication between our two matrices. We are going to be multiplying the inverse matrix, which is namely that matrix in out 6, times your original matrix. When we matrix multiply these matrices, we do get an identity matrix to be outputted, which is our desired result when multiplying an inverse times its matrix. If we wanted to yield a solved linear system, We can absolutely do that using that NumPy linear algebra module, but we are going to be accessing the solve function this time. You are going to plug in a matrix. We have our matrix 1, 1, 1, -1, and we are being asked to solve the linear system of what times the highlighted matrix equals the vector 20, 40. So we are looking for a x vector, if you want to call it, to solve what ax equals b, where the highlighted vector is b. We do get this array to be outputted 12, 8. So what this means is if we multiply our highlighted matrix times the vector 12, 8, we will get out the b vector of 24 as output. Let us go ahead and create a matrix and save it into a variable. We are going to be creating a 3-column, 2-row matrix and naming it A. And we do, in fact, get the matrix seen in Out 9 with row values 1, 2, 3, then the next row, -1, 0, 1. We can yield the covariance matrix of A by doing the following arithmetic. We are going to be accessing the shape of A, which is going to give us 2 elements in order of their dimensions. The dimensions in Python will give you row by column, so this index of 1 is actually going to give us the second element in that output array. So we are going to be grabbing the number of columns of A. And we are going to be doing 1 divided by the number of columns in A times A transpose. That is what this dot T notation means. It is just a very simple, easy way to find the transpose of your matrix. We are going to save this as covum, and then in order to produce our covariance matrix, we are just going to reiterate that variable name, and we do in fact get a covariance matrix seen in Out 10 in the highlighted text. We can also yield a new vector in a different direction than our vector that we have. We are going to set our variable u equal to our matrix. So this matrix is just a row matrix, 1-row matrix of 1, -1. But we are going to transpose this row matrix. So now U is going to be a vector matrix of 1, -1. We can multiply our previously stated covum variable by U and make it equaling to V. This will produce a V vector where our V and our U are in different directions. You can see that in Out 11 that our V matrix is the vector for 0, roughly. This does, in fact, tell us that they are in different directions. We can yield the eigenvalues and eigenvectors in one output using the function found in that linear algebra package within the NumPy package. You're just going to plug in your matrix into the parameter of the Eig method. We could go ahead and set the output equal to U. We're just using this variable name to tell us that we have eigen parameters in this U variable. In order to get your eigenvalues from this U output, we are going to access the first element with index 0, seen in the highlighted text. We get 2 eigenvalues to be outputted from our Covariance matrix, namely seen in out 12. If you wanted to yield the corresponding eigenvectors for these eigenvalues, you're going to access the second element of that U output, which could be seen with index 1, and we do in fact get a 2 by 2 matrix outputted where the columns correspond with the eigenvectors of the eigenvalues we received in out 12. In order to verify the eigenvalues and vectors, we can do a little bit of computation in order to see if we get the desired eigenvectors out. We are going to multiply Covariance times our eigenvectors matrix divided by our eigenvalues vector. This computation does output the highlighted matrix. One thing to notice about this highlighted matrix is it does match up with our eigenvectors matrix seen in out 13. This was the desired result. We just wanted to verify our eigenvalues and vectors. Next, we will be going into an SVD representation model for space-time data. The first thing that we are going to be doing in order to do this SVD representation is creating a 2 by 3 space-time data matrix for the SVD. We're going to use that map function, and we are going to create Matrix A, which can be seen in the highlighted text. Next, we're going to want to perform the SVD calculations. We're going to go into that NumPy package, accessing the linear algebra module, and then finally using the SVD method on our matrix A. We're going to save this output as MSVD. So now MSVD does hold all of our SVD calculations that were found from our matrix A. In order to yield the D vector in SVD, you're going to access the second element, which can be done using the first position. We do get a D array outputted in output 16. Next, if we wanted to yield the U matrix in SVD, we would just need to access the first element of the MSVD output, but we are going to transpose this output and set it equal to our U. We do in fact get a U matrix seen in the highlighted text. And lastly, if we wanted to yield the V matrix of the SVD computation, we would have to access the third element with position 2. The SVD computation in Python does introduce extra elements in your V matrix. So the highlighted line is not necessary, but it does help the reader better understand the computations that are going into the SVD decomposition of our matrix A. So once we do run that line, we can print out V, and we do get a 3 by 2 matrix as our output for V. Next, we can verify that A equals U times D times V prime, where V prime is the transpose of V. So the first thing that we want to do is we want to make our D array into a matrix. We are going to be using the diag function in order to make the values of D into a diagonal matrix. We're going to transpose V by using that dot T notation on our V, and we're going to save it as VT. Next, we can verify our SVD result. We are going to verify it doing the computation U times the diagonal of D times the transpose of V. And we're going to save this result as very M, basically verifying my matrix. So if we wanted to just round those values that are computed in very M, we could just do NumPy matrix with a round method on the matrix we are looking at. And we do, in fact, get our original matrix A to be outputted, as seen in Out 19. This is one way you can verify your SVD decomposition. Next, we are going to yield the covariance of our matrix A using the arithmetic that was explained earlier. We are going to be doing 1 divided by the number of columns that is found in matrix A times our matrix A times the transpose of our matrix A. And we're going to name this variable covim. This is going to be the covariance of our matrix. If we wanted to yield the eigenvectors and values of matrix A, we're just going to use that eig method that is found in that linear algebra package. We're going to name this result eigcov. So this is going to be the eigenvectors and values of our covariance matrix of A. If we wanted to look at the first element of our eigcov variable, which corresponds with the eigenvalues of the covariance matrix, we do get eigenvalues 4.77 and 0.55. If we wanted to yield the eigenvectors of matrix A, we do have to access the second element with the first position in that eigcov output. We do get a matrix outputted which corresponds with the eigenvalues that we found using the highlighted text. So eigenvalue 4.77 has the eigenvector 0.98, 0.16. We can verify these eigenvalues with our SVD. We are going to square our D matrix, and then we are going to divide it by the number of columns in our A matrix. We do in fact get our eigenvalue array to be outputted, which verifies our eigenvalues with our SVD decomposition. Lastly, we can yield the true eigenvalues of matrix A using that 0th position in our eigcov variable, and we do in fact verify our eigenvalues with our computed eigenvalues. This concludes our section on matrix algebra and an SVD representation. In the next video, we will continue with Chapter 4, but take a closer look at the Southern Oscillation Index.